Hi, my name is Zhu Mengqi from Columbia University. Here is my final project for the course Applied Deep Learning, Detecting Cancer or Pathology Images. I work on the data CAMYOUNG16. It's a huge dataset of images collected independently from two medical centers in the Netherlands. My goal here is to develop a model based on this dataset that outputs a heat map showing regions of a biopsy image likely to contain cancer. The first part is loading data. Here I only use the slide Tumor 0191. This is the original biopsy image, and this is a truth mass image where the black area means the tumor area. Here we can see there cannot be any tumor if there is no tissue, so we can use the trick to train the samples only for the images that contain tissues, so we can reduce computation cost. As we can see, the dimension of level 0 is too huge, so I consider downsampling to break this huge image into patches 224 by 224 for training. The reason I choose 224 by 224 is that first it yields 40,250 total patches, which is a reasonable size. Second, it's the default input chip for VGG16. Here is the code I break the huge image into patches. Here's the code I generate the image. Here I got some example patches from the image, and here are the corresponding truth mass of the patches, where here white means the tumor area. As you can see, it is unbalanced data. The patches which contain tumors only 6.7%. This means if I design a model that classifies all the patches to non-tumor, I could get an accuracy of 93.3%. This baseline is so high. So I sample 4,044 patches from non-tumor patches and include all 956 tumor patches. When dividing training data, validation data, and test data, I used stratified shuffle split to ensure each set to have the same proportion of tumor patches. The second part is training model. First, I tried a small size of 1,000 training samples and 200 validation samples with fine-tuning with VGG16 base. I unfroze the layer block 5 conv1 to make the model the pre-trained model better fits my data. Here is the result. We can see that there is overfitting even if the epoch is only 5. But the accuracy is good. So I consider training from scratch, just make some adjustments from VGG16. Because VGG16 is trained on a very large dataset. So for here, my dataset is only 5,000 training samples. So I consider simplify the VGG16 to solve the problem of overfitting. Here I used all 5,000 samples and divided into train, validation, and test set. Here are the results. We can see the overfitting issue is greatly solved, and the accuracy is better. The third part is model evaluation. I test model on the test sets and get results like this. The accuracy is 96%, which is quite decent, which means given one grid, there is 96% probability of correctly prediction. The recall precision and F1 score are also listed, but I think from medical view, for classification of detecting cancer, except for accuracy, we are more interested in false positive and false negative. Here, the false positive is 0.01, which means if the model detects tumor, there is 1% probability that it actually does not contain tumor. The false negative is 0.03, a little bit higher, which means if the model does not detect tumor, there is 3% probability that actually it does contain tumor. So we should be more careful when the model says it does not detect tumor. Next, I would like to show my result of prediction heat map. Here is one example. Here the white area means it contains tumor. And for here is a prediction heat map, while the red area means there is a higher probability of containing tumor. And the blue means there is a very low probability of tumor. We can see the two correspond to each other. Next, I would like to show my result on the whole slide. On the left is the model predictions heat map, and on the right is the truth image. We can see that my prediction heat map basically shows all the area of all the tumor areas in the truth image. That's all for my final project. Thanks for listening.